At last, we've come to this magical chapter in which all of your questions about the universe will be answered. For instance, where babies come from, how food turns into poo, and why is it that every time I wait in line at a supermarket, there's always someone in front of me that has some purchase that is so complicated that it's almost like a hostage negotiation. Yes, indeed, this is Chapter 19, in which we will talk about chemical thermodynamics. First, I want to share with you Scumbag Teachers of the Day. The first one says, "You don't talk much? Don't worry, I'll break you out of your shell." It's funny because I used to be that teacher. The second one says, "Every single student failed the test. You obviously didn't study enough." After this series of videos, which will cover sections 1 through 7, basically all of Chapter 19, you guys should be able to determine if a process is entropically spontaneous or non-spontaneous, know the first and second laws of thermodynamics, calculate delta S for phase change, calculate delta S for expanding gases, determine if a process has a positive or negative delta S value by looking at it, know the third law of thermodynamics, calculate delta S naught for reactions and physical processes, calculate delta HF naught, or the enthalpy of formation for reactions and physical processes, calculate the Gibbs free energy change, or delta GF naught, for reactions and physical processes, and use them to determine if a process will be spontaneous or non-spontaneous, and use Gibbs free energy change to calculate a reaction's equilibrium rate constant, or K. That's the lineup. Let's get started, beginning with the first law of thermodynamics. Back in Chapter 5, to which I'll link here, we learned that the first law of thermodynamics says that in any physical process, energy is conserved. That is, that any energy lost by a system must be gained by its surroundings and vice versa. In other words, energy doesn't just simply disappear. This idea can be expressed mathematically as delta E, the change in energy, is equal to Q plus W, where Q is heat and W is work. Pictorially, our text uses this analogy. It imagines the amount of internal energy that you have as being like money inside a safe at a bank. If your internal energy gains heat or work, that is a deposit being done on your system. That represents specifically a gain of heat, or Q being greater than 0. That would be what we would see in an endothermic process. Now, endothermic processes, if we're near them, feel cold. For example, melting ice in your hand feels cold because it is endothermic, and the reason is because it is sucking heat out of your hand and depositing that heat, metaphorically speaking, into its own bank account. Endothermic. Now, in contrast, if you have a process that loses heat or does work on its surroundings, that's one where you have Q being less than 0. That would be, enthalpically speaking, an exothermic process. When I'm near a reaction that gives off heat, such as the detonation of dynamite or a lighting of a fire or combustion of fossil fuels, that is an exothermic process because it's giving off heat to its surroundings. It is losing internal heat from its metaphorical bank account. I hope that analogy helps simplify things. If not, you can totally throw it under the rug, the metaphorical rug, and we'll go on by discussing spontaneity. A spontaneous process is one that proceeds on its own without any outside assistance. Thermodynamically speaking, a spontaneous process occurs in one direction only, and the reverse of any spontaneous process is always non-spontaneous. For example, dropping an egg, as shown over here, and watching it shatter is an example of a spontaneous process. Once it starts, it occurs without any outside assistance, and it's also non-reversible, as you can well imagine. Now, another example of a spontaneous process is the transfer of heat from a warm solution to its cold surroundings, or vice versa. Heat always likes to go thermodynamically downhill, from whatever's warmer to whatever's colder. Another example of this would be your home. If you have a heated home in the winter, for example, it's always going to be warmer inside than it is outside. However, if you turn off the heat source, the heat inside your home will spontaneously dissipate, seeping through the walls and cracks of your home to the outside until the temperature inside equals the temperature outside. Once again, heat always likes to dissipate or go thermodynamically downhill. That is spontaneous, and the reverse of it would be non-spontaneous. This takes us to an example problem. Predict whether each of the following processes is spontaneous as described, or SAD, spontaneous in the reverse direction, or absurd, or an equilibrium. Here's the first one. Water at 40 degrees Celsius gets hotter when a piece of metal heated to 150 degrees Celsius is added. The next one, water at room temperature decomposes into H2 and O2. Next, benzene vapor, whose formula is that, at a pressure of 1 atmosphere condenses to liquid benzene at the normal boiling point of benzene. Now I want you to think about each of these processes and determine for yourself if it's spontaneous as it's described, or if the reverse of it would be spontaneous, or if it's just an equilibrium setting. I'm not going to answer it for you, but want you to wrap your head around it on your own. We'll now talk about the second law of thermodynamics, which says that in any spontaneous process, entropy or disorder must increase. As we mentioned earlier, the first law of thermodynamics says that energy is always conserved. That is, it just doesn't just disappear. That, however, is not true of entropy. As it turns out, entropy always increases for any spontaneous process. There's one more detail we have to consider. Spontaneous processes are irreversible. Hence, another way of stating the second law of thermodynamics is to say that entropy increases for irreversible processes. For reversible processes, entropy change is 0. So, an additional implication of the second law of thermodynamics is that entropy of the universe is always increasing. As we learned back in Chapter 5, the entropy of any system will always increase unless energy is put into it. However, that input of energy always causes an increase in entropy somewhere else. Hence, the overall entropy of the universe is always going up. Living organisms are quintessential examples of our fight against entropy. As we look at living organisms, we are, frankly, quite organized, molecularly speaking. That is, we are at low entropy. How do we obtain and retain or keep that low entropy state? By causing an increase of entropy somewhere else. Ultimately, the energy that we use all comes from the sun in the end, and the sun is continuing to experience an increase in entropy as its constituents in the nuclear fission reactions that are keeping it heated gradually go closer and closer to its death. Well, on that depressing note, I just have to ask, when we consider the import of the second law of thermodynamics, I wonder what philosophical implications these facts might have. As it turns out, there are a number of ways to calculate the entropy changes of physical processes. In general, for any physical process, the entropy change, or delta S, can be summarized as, or is equal to, the final entropy state minus the initial entropy state. We can also calculate delta S for any process involving the reversible transfer of heat, abbreviated here as Q reverse, by using equation 19.2 from our book, which is this one. The delta S of fusion is equal to Q reverse divided by T. Freezing, also called fusion, is a reversible process. Hence, this term is also equal to the delta enthalpy of fusion divided by T. Because for reversible processes, Q and delta H, heat transfer, are the same. That takes us to a problem. The element gallium freezes at 29.8 degrees C, and its molar enthalpy of fusion is this number. What is the value of delta S when 60 grams of gallium solidifies at 29.8 C? As I usually do, I'm going to allow you to attempt this on your own if you like, and then if you want, you can click the link here to a separate video in which I show you how to do it on the board. Here's another one. Elemental mercury is a silver liquid at room temperature. Its normal freezing point is that number, and its molar enthalpy of fusion is this number. What is the entropy change of the system when 50 grams of mercury freezes at the normal freezing point? You can use the information from the previous example to attempt this on your own, and then, if you like, you can click the link here to a separate video in which I'll show you how to do it on the board. That takes us then to delta S for expanding gases. We can also calculate delta S for a gaseous system in which the volume is changed. This is done by using equation 19.3 from our book, which our authors cleverly hid in a box at the top of page 792. This equation, derived by combining 19.2 and the ideal gas law, says this, that the delta S of any system is equal to N times R times the ln of V2 divided by V1, where N is the number of gas moles that are present in the system, R is the ideal gas constant, in this case 8.314 joules per mole Kelvin, or joules per mole. V2 is the final volume of the system, and V1 is the initial volume of the system. With that said, let's look at a problem. Imagine that the volume of a chamber containing 0.2 moles of an ideal gas at 27 C is increased isothermally. That means without any transfer of heat to or from the system, from 10 liters to 18.5 liters. What's the entropy change for the process? I invite you to attempt this on your own using the equation I just showed you, and then if you like, you can click the link here to a separate video in which I show you how to do it on the board. Now, is delta S positive or negative? Well, as we've learned so far, entropy is the amount of disorder in a system. If a system becomes more ordered during a physical process, then its entropy decreases. That is, it has a delta S that is negative. If it becomes more disordered, then its entropy increases. That is, it has a delta S that's positive. We should remember that because of the second law of thermodynamics, any entropy decrease or negative delta S can only occur by increasing the entropy of the universe somewhere else. Now, we generally expect entropy to increase for processes in which solids are converted to liquids or ions, solids or liquids are converted to gases, or the number of gas molecules increases during a chemical reaction. Now, if you think about it, every single one of these scenarios is one in which molecules go from being more constrained or restricted to being less constrained and less restricted. In other words, they go from being more ordered or organized to being less ordered and more disorganized. Hence, every one of these is a scenario in which entropy is increasing because disorder is increasing. I invite you to think about them just so that you can wrap your head around this subject. You should also keep in mind that while the change in entropy, or delta S, can be either positive or negative depending on the process, any system's actual entropy value, S, will always be positive. In fact, S can never be negative. It can only become 0. That takes us to a problem. Delta S is positive for which of the following reactions? I'm not going to answer this for you, but will give you some advice. I want you to look at each of these processes and try and ask yourself the question, am I becoming more disordered as I go from left to right? If the answer is yes, then it is a positive delta S. If you're becoming more ordered as you go from left to right, or more constrained, then it's a negative delta S. Also, you might look at examples like A, for instance, where I've got gas molecules on both sides. That might be hard to imagine. Am I becoming more ordered or more disordered? Well, you'll notice in the case of A, I've got 1, 2, 3 total moles of gases on the left side of the equation, while I only have 2 moles of gas on the right side of the equation. So I'm going from having 3 moles of gas to having 2 moles of gas. Is that an increase in disorder? Heck no, because gas molecules are super disordered. If I'm reducing the number of gas molecules from 3 to 2, I'm actually becoming more ordered. So process A would have a negative delta S. You can use the same logic for other equations here that have gases on both sides. I'll let you look at the others and see if you can figure them out on your own. That takes us to another question. Delta S is negative for which of the following reactions? Once again, a negative delta S is a scenario where things are becoming more ordered as you go from left to right. I want you to look at each of these and see if you can determine that on your own. All right then, here's another detail I want you to know. When comparing any two gases, S, the absolute entropy value for that gas, increases with molar mass, according to page 801 of our text. Now, keeping that in mind, let's do one last problem. Of the following, the entropy of which is the largest? Now, based on the information that I just told you, see if you can answer this on your own. That takes us to the end of this video. Please stay tuned to my next series of videos in which I'll continue teaching you about chemical thermodynamics. Until then, have an enjoyable rest of your day.